Question 3 is to do with titration. So we have dilute sulfuric acid is labeled L. We uses apparatus A to measure and transfer 25 cm³ of the L, which is the H2SO4, into apparatus B. So this is a 25.0 cm³ pipette. This is a 500 cm³ volumetric flask. This is what your lab technicians would use to prepare solutions for your titration experiments. And because if you're just one student, you only receive one small bottle. But imagine if there are 100 students, then the technicians, the lab tech, will actually have to use more than 500 cm³. Usually they'll prepare like 5 liter or 10 liter of solution. Huge amount of solution. It takes a huge amount of skill as well as huge amount of effort to actually shake the solution, because if you make up the solution, you actually have to shake it vigorously in order to ensure that everyone who get the solution from this batch would have consistent and uniform, would have solution of uniform concentration. All right, so name apparatus A. So it's a pipette, but I would probably write 25.0 cm³ pipette because the volume is given there. Name the other piece of apparatus that should be used. So a pipette doesn't suck out any liquid on its own. You need a pipette filler in order to put on top of it, and then you will press on the I think like I just started making some tutorial videos on actual practical, so you can watch that tutorial video and see the pipette filler and how I actually have to press the button A to suck in some A, and then once I snuck in the pipette filler in the glass tube here, the glass end of this pipette, then I'll press S to suck the liquid in from the solution that I want to suck it in. Okay, so this is called a pipette filler. It's very hard to explain titration to someone who has never done titration before, and therefore I recommend you to actually watch a tutorial video such as the one I just posted, or there are many other tutorial videos on YouTube as well, so you don't necessarily have to watch that one. Okay, why is apparatus A used instead of measuring cylinder? So this has accuracy, alright, so it's 2.0. Why didn't they write 25 cm³? Because this is more accurate than 25 cm³. 25.0 is actually more accurate than just 25 cm³. So it's to do with accuracy. So apparatus A is way more accurate. It's more accurate at measuring volume, which is 25.0 cm³ than measuring cylinder. So measuring cylinder might be more accurate than a beaker, but measuring cylinder is not more accurate than a pipette or burette. Now the student make up the solution with distilled water in this apparatus B called a 500 cm³ volumetric flask. This is solution M. So I'm pretty sure that you don't really need the volume, but I just choose to write down the volume because the volume was actually given in the question, and sometimes in A level they actually ask you describe how would you prepare a solution of blah 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 blah. Therefore we have to mention the quantity as well as the name of the apparatus itself. Now the student transfers that much of that M, which is the diluted H2SO4 that you just make up, and adds 2 drops of methyl orange. So methyl orange in sulfuric acid into a conical flask. So this is in a conical flask. The conical flask contains the diluted acid, which you add in the methyl orange, which means this thing goes in the burette. This is the NaOH aqueous. It goes in the burette, and you run the titration until the indicator changes color and you reach the end point. So the burette, immediately before it is filled with R, so first of all you wash the burette with distilled water if it is not clean. Alright, distilled water, because distilled water contains no other dissolved ions, because dissolved ions can affect your titration experiment. But before you fill it with the R, which is NaOH, you must also wash away whatever remaining distilled water you have with R itself, because if you have water remaining in the burette, it can affect the concentration of R, and therefore it can affect how much volume of R that is required for titration. That's why it's important to flush the burette and wash it with R before you actually use it and fill it out for titration. So you actually have to fill it with R, which is the 0.100 mole per dm cube, NaOH aqueous. Okay, so what's the color change of the indicator at the end point? This is inside the conical flask. The methyl orange was added to the sulfuric acid in the conical flask. So methyl orange in acid, so it will go from methyl orange in acid. Of course, that is not what you put in, because that is just my indication of what I'm thinking in my brain. Methyl orange in acid will give me a color of red, or sometimes they look pink, all right, and then it will go to orangey yellow. Okay, orange, or you can say yellow, at the end point when the acid has been neutralized by the base. All right, so the student does 3 titrations. The diagram shows part of the burette with the liquid levels at the beginning and at the end of each titration. Because these acids are actually colorless, that's why we needed the indicator to show the color change. There are some titrations that don't require indicator, such as the such as the redox titration, acidified KMnO4 and reducing agent. Then the really deep purple of that KMnO4 will actually go pale pink or really colorless towards the end, and that is self-indicating, but not for this type of acid-base reaction. Yeah. So for titration 1, initial burette reading, initial mean at the beginning. So this is at the beginning. You read from below the meniscus. Be very careful. You read from below the meniscus. What am I doing here? 1, 2, 3, 4, 5. Okay. So this is 1. You can see there is a bit of a longer line there. 1. So this is a bit of a longer line. So this is 0.50. Just 1, 2, 3, 4, 5. So this is exactly 0.00. Okay. So this is exactly 0.00. I'd like to just highlight the point that burette actually has an accuracy of plus minus 0.05 cm cube. So this is the accuracy of burette, and if you are doing an O-level practical or IGCSE practical, they actually say always in the marking scheme that you give your answer to the nearest 0.1 cm cube, and that's acceptable in IGCSE and O-level. That doesn't mean that you are wrong, it's just that the level actually expects you to give it to plus minus 0.1 cm cube. But in A levels, we actually have to tell the students that burette is accurate to this, because they have to do percentage error calculation. And because the percentage error calculation involves you knowing the accuracy of burette, it means that it's good to actually practice writing in the volume of burette reading to the nearest 0.05, meaning to say to the nearest 2 decimal place. So the next reading will be 0.05, the next reading will be 0.10, and so on and so forth. Okay, so just because the marking scheme says you expect a 1 decimal place, I will really teach my students to actually write it to 2 decimal place, simply because that's me, and simply because the person who is marking our paper will be a chemist as well, or chemistry teacher, and any chemistry teacher who is sensible enough and qualified enough would be able to tell you that, you know, marking scheme is for the examiners. It does not take away the chemistry skill of the people marking your paper who knows chemistry inside out, obviously. All right, so I'm just telling you that all my tutorial videos will definitely use 2 decimal place burette reading, and if you're not happy with that, by all means, okay, you don't have to follow it. But you know, in the future you might be severely affected in A levels. You might have to rechange your mindset all over again. All right, so the final burette reading, read below the meniscus. So this is 22, this line there is 21.5, so this is 21.50, remember 2 decimal place, 21.40, 21.432, 21.20. Okay, so take away the difference. Your calculator when I do this, your calculator will show you this, and this is one of the many mistakes because you're not following through the level of accuracy. Okay, so titration 2, this is 23, so this is 22.9, 22.8, 22.7. Hang on, that is initial. Okay, so what is my final then? This is my long line. There's 44, so there's 43.9 below the meniscus. And if I just finish reading all of them first, so this is 10, 10.1, 10.2. So 10.2 is the initial reading, 10.20 is the initial reading. This is 30.50, so 30.60, 30.70, 30.80. So be very careful what is final and what is initial, and that's one of those things that a lot of students would, well, sorry to say, but not a lot of students, some students I should say, would make the mistake of not following through. Alright, so it's 20.60. So looking at this, I can definitely tell this is way off, and I don't really like the way this student has done it, because I will always advise students to do a rough titration, because what is the point of being exact from the very first one when you don't even know where you're supposed to be looking at? Okay, so have a look at my other tutorial videos on titrations, and you will know exactly what I'm saying about the importance of actually doing a rough titration. If you don't know where to fish, you'll just be wasting time doing drop by drop wherever it might stop. Okay, so it's about getting a feel, and then when you do the exact titration, you're not wasting too much time. Okay, well, at least that's the skill that I think is important. It might not be important to you, maybe not now, but eventually when you do A-level chemistry, you definitely have to do practical as well, because there's no alternative to practical for A-level chemistry. So here, this is definitely way off these two consistent titles that are within, well, in fact, they're exactly equal. Okay, so I know in all level or IGCSE, they actually accept concordant titles within plus minus 0.20 cm3. But let me just remind you, okay, because this video might not necessarily be just useful for all-level students, IGCSE students. The level of accuracy that A-level students will be expected of will be plus minus 0.10 cm3. So it's important that when you do a titration, you want it to be as close as possible and not by this much. Okay, but this is the extent to which all-level IGCSE students would be marked a little bit more leniently than you would be when you proceed to do a more advanced level chemistry course. They're expecting you to be more skillful in doing titration. Okay, so tick the best result. I just did. Use the tick values to calculate the average volume. So when you average the volume of the two things that you tick, so when you press that into your calculator, your calculator will show you 21.2. But again, it's all about the carrying through the idea of 2 decimal places for burette reading. When you average burette reading, it will also be 2 decimal places. All right. Just because the calculator does not show you, does not mean that it's not there. The level of accuracy comes from within you. Do you know your experiment or not? Why was it unnecessary for the student to do a third titration? So this student had done a third titration, but it shouldn't have been necessary, because he have already obtained 2 titles that were consistent. In fact, they were equal. Okay, so I guess if I were you, I would really be thinking about consistent and concordant titles that are within this, because this is a more higher level accuracy than this, which should be what you're looking for in the real titration anyway. Okay, so because the student already achieve or obtain consistent, do they use consistent, or you can use concordant titles plus minus 0.10 cm3 in the first 2 reading, in the first 2 titrations. So you don't really need a third titration because they were already fairly accurate, right? Okay. Solution R is a 0.100 molar. So big M refers to molar and molar refers to mole per dm cube solution. Calculate the number of mole of NaOH in the average volume of NaOH required. Remember the average volume that you calculated, that belongs to R, and R was sodium hydroxide, 0.100 mole per dm cube. So this is mole per dm cube. When you multiply by the volume of the sodium hydroxide, which was R, in dm cube, so this was in cm cube, you need to convert to dm cube. You multiply by the concentration of itself, then you can get the mole. All right. So in all of my other stoichiometry and mole calculation video, you will see me using small n to represent mole. I label it because what is n, what is mole? A lot of students will just write mole, 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 you know. At the end of the day, if you have to look back at your work, if you have to rethink what you did, that means you have not done a very good job at labeling your stuff. That's why I always like to do my bookkeeping very clearly, because I am very forgetful. I make mistakes. I'm not a very good chemist. So, you know, I always have to remind myself what I'm doing, okay? So it's 0.100 mole per dm cube. So I like to follow through with the units. I can very clearly see this is dm cube, and I very clearly see that this is cm cube. The average volume of this sodium hydroxide is 21.20 cm cube. So 21.20 times 10 to the minus 3 dm cube. You might also realize that what in the world is he doing with 10 to the minus 3? Well, you know, 21.20 cm cube, when you convert it to dm cube, is divided by 1000 dm cube. And if you do maths at all, you will know that it's the same as 10 to the minus 3. It's just a neater way of writing over 1000, a different way of writing it, but this is just maths instead of chemistry. So I don't want to spend too much time explaining why I actually did this, but well, you can see why I did it. I hope that was clear going forward, that you might see in most of my tutorial videos, instead of me writing over 1000, 10 to the minus 3 multiplied by 10 to the minus 3 is the same as the volume divided by 1000. So 0.100 times 21.20 times 10 to the minus 3. Your calculator show you 2.12 times 10 to the minus 3 mole. So very straightforward for that 1 mark. And they want your answer to 3 sig fig. So this is happen to be exactly 3 sig fig. Alright. Dilute sulfuric acid reacts according to the equation here. So 1 mole of sulfuric acid reacts with 2 mole of NaOH. So what is the mole of H2SO4 in 25 cm cube of M? Remember, this was M just now because you diluted the original sulfuric acid. You diluted the original sulfuric acid, okay? And you take out 25 cm cube from the diluted sulfuric acid. So this is the diluted sulfuric acid that reacts with that. And we know how many mole of sodium hydroxide was in the titration. So the mole of sulfuric acid is to the mole of NaOH. I will always write like this: label mole, label mole. It can be the other way around, doesn't matter, because we are doing fractions and we're doing ratio. Doesn't matter if it's the other way around, you will still get the right answer provided you know what you're doing. I have put the mole of sulfuric acid on top, so I'll have 1 on top from the balance equation. If I have gotten it the other way around, doesn't matter, it'll be equal to 2 over 1 from the balance equation itself. 2 mole of NaOH reacts with 1 mole of H2SO4. 2 mole of NaOH reacts with 1 mole of H2SO4. On the right hand side, I'll put the actual mole that reacted. Okay, I want the actual mole of sulfuric acid that reacted. So this is the actual mole of sulfuric acid that reacted, and at the bottom will be the actual mole of sodium hydroxide that reacted, which voila, it was from the previous part of the question. This is mole over mole, this is mole over mole, this is mole over mole. Okay, so the maths is solid there. All right, so there's nothing wrong with the maths there. That is why this level of bookkeeping is always desirable. So move this up there, and I have just swapped onto the other side, but move this up there and divide by 2. And because we had 3 sig fig for the previous part, we are maintaining the same level of accuracy. So there's 1.06 times 10 to the minus 3, and that was in 25 cm cube of M. Now the one in 500 cm cube of M. So remember when you have 500 cm cube of M, and then you take out 25 cm cube, alright, and that was 25.0 cm cube actually. So what actually happened here? You take out 25 cm cube from this, well, from this diluted sulfuric acid, right? Okay, so going from left to right, all you did was you take out. Okay, so the mole is different. But you take out this thing from the bulk of the solution that you just made up, the concentration is the same. So I know the mole here is in 25 cm cube. What is the mole in the 500 cm cube? It's going to be a lot more, but the concentration is the same. Alright, so this kind of thing is like a very common in A-level titrations, but not so common at O-level, but you need to keep an eye out for simple diagram like this. Simple diagram helps. I'm not a great artist, but I like to draw simple diagram like this so that I can see, I can visualize, I can think what is different and what is the same. The mole is clearly different, so you cannot have the same answer. I have the same concentration, but how much bigger the volume is going to be how much bigger the mole is. So you can be thinking about, since the concentration is the same, 25.0 cm cube give me this much mole. Alright, because the concentration is the same, right? So when I have 500 cm cube, my mole is going to be a lot bigger. By what factor? By 500 divided by 25.0. I think it's around 20 times bigger. So that is 0.0212 mole. Okay, the unit is given there, so I don't need to write mole again. Now calculate the number of moles of H2SO4 in 25.0 cm of L. So just now this one comes from L, so perhaps I need to draw another diagram. So this is 25.0 cm cube of L. This is the concentrated acid. Then I add water, then I get the diluted acid. From the diluted acid, I take out 25 cm cube into here. So we need to be concerned about what is different and what is the same here. Here, which is actually for this part of the question. Here, this is important for this part of the question. So what do we have here? From here to here, I am doing dilution. Just add water. Well, in fact, just add distilled water. When you just add distilled water to this concentrated acid, you are not taking anything out. You are not putting anything in apart from just adding water. So the mole of the acid is the same. The mole is the same. What is different? Concentration is different. So you need to see what is different from this step to this step. This here, the mole is different, but the concentration is the same from here to here. From here to here, the mole is the same, but the concentration is different. So now we know the mole in here, but the mole in here is the same as the mole in here because I'm just adding water. Alright, so the mole of H2SO4 in 25.0 cm cube of L is equal to the mole of H2SO4 in 500 cm cube of M. Because I'm just adding water, the concentration is different. I've just done dilution, but the mole is the same. I have not added sulfuric acid in. I've not taken any sulfuric acid out. The previous part of the question, tell me this bit, the mole of sulfuric acid in 500 cm cube of M. So that's 0.0212. And that's it, really. I mean, that follows down to this. Okay, so the mole is the same. And therefore, what is the concentration of H2SO4 in L? So you have 0.0212, which is this one, which is equal to this one, is going to be the concentration of H2SO4 in L times what is the volume that you have in L, which is 25 cm cube. So it's 25.0 times 10 to the minus 3. So this is in mole per dm cube. This is in dm cube. That's why I have divided by 1000 mole per dm cube. Alright, so this is mole. So the concentration is going to be that divided by 25.0 times 10 to the minus 3. So I get 0.848. Don't forget units. Units is very important when you're doing calculations, especially where they are relevant. Okay, so they all maintain three significant figures still. And that was it. That was the last bit of the calculation, and we're just left with a bit of structured bit here. So between each titration, between every titration, because you might only be given 1 or 2 conical flasks, you wash the conical flask with water and dries it. Assuming this is water, you should always use distilled water afterward. Okay, so a second student repeat the experiment, but you uses L instead. What is L? L is the concentrated H2SO4. Your titration just now was using M. Your solution was using M. So your titration was using the diluted solution, but you wash it with the concentrated L. Okay, so L is the concentrated solution of H2SO4. So because you wash it with concentrated solution H2SO4, then inside your conical flask you have extra mole of H2SO4. If you have extra mole of H2SO4 in your conical flask because you did not dry your flask, this is important. Extra mole of H2SO4 in the conical flask would mean extra mole of NaOH is required. And because your NaOH concentration in the burette doesn't change, if you need extra mole of NaOH, therefore you need extra volume of NaOH, meaning the titration volume would be larger. And it's state and explain. So I just explain first. Alright. So L is the more concentrated. H2SO4 aqueous doesn't matter, because the student forgets to dry the flask. Extra mole of H2SO4 in the conical flask means more mole of aqueous NaOH is required for neutralization. And because the concentration of the NaOH in the burette is the same, therefore greater, tighter. Tighter refers to the titration volume of NaOH is also known as tighter. That's why they say choose the best tighter, because tighter refer to the titration volume. Greater tighter means greater volume of NaOH required. So that is just stating, is it smaller, larger? So it is going to be larger, or you can use the term greater, tighter volume. Alright. Finally, a third student repeat the experiment, but this time your conical flask, you wash it with water, presumably distilled water again. Alright, because distilled water contains no dissolved ions, whereas your tap water might contain dissolved ions. Okay, moreover, a lot of the water are provided in wash bottles in the lab. The wash bottle does not contain tap water, but rather distilled or deionized water. Does not dry the conical flask, but it's just water. Alright. State and explain whether it will be smaller, larger, or unchanged compared to the student titration volume. So again, the conical flask has the acid. The acid is what you pipette out. You pipette 25.0 cm3 because that was the apparatus you used. I think I mentioned all this in that tutorial videos on the actual practical, although the actual practical actually only covers acidified KMnO4 and iron 2+. I did specifically go through what would happen, why we wash it with this particular reagent instead of distilled water, why did we wash the other thing with distilled water instead of the reagent itself. Okay, it's all thinking about what actually remains in the conical flask. Okay, so in this case, again, 2 bits to it, so I'll probably explain first. In this case, the little bit of water, presumably distilled water, remaining does not change the total mole of acid pipette into the conical flask. Because when you pipette the acid, you pipette exactly 25.0, right, and you put it into the conical flask. Yes, it might affect the concentration once you put it into the conical flask, but you will drop everything in the pipette into the conical flask, meaning to say that all the mole of the acid from 25.0 cm cube, all the mole of that acid would go into the conical flask, and the mole will remain the same because you are just having a little bit of distilled water. All right, so does not change the total mole of acid prepared into the conical flask, and since there's the case, therefore this will not require any more or any less mole of NaOH for neutralization. And if that is true, since the mole of acid is still the same, the mole of NaOH required for neutralization is still the same, therefore unchanged titer volume. Titer volume refers to the titration volume of the NaOH from the burette, because your mole of acid is exactly the same. It's just less concentrated if you have a little bit of water, but it's not going to affect the mole of acid that you prepare in. Therefore, it's not going to affect the mole of NaOH for neutralization. That's why when you wash your conical flask after each run, you wash it with distilled water. If you are left with a little bit of distilled water in there, it really does not matter. It will not affect your titration result, because it's just a bit of water, and because of this exact reason, it does not change the mole of the substance that you prepared into the conical flask, and therefore it will not affect your titration volume.